Hello class, welcome to this video on Calculus 1. So we're introducing the concepts of calculus here. Now this video series is going to include content from Calculus 1 to 3. So as we proceed through the series, we'll have Calculus 1, Calculus 2, Calculus 3 concepts. So let's go ahead and introduce the ideas of calculus. So what is calculus? Calculus is the mathematics of change, and it's usually dynamic. So what it takes, if you recall, if you've taken a pre-calculus course, you know that maybe at the end, you may, depending on time, have gone over the idea of limits. And so what it does is you take the concepts of pre-calculus, maybe algebra 2, any concepts that you had prior to calculus, and instead it generalizes it with the use of these limits. So if I take these concepts of pre-calculus, for instance, and I go through this limit machine, is what I call it. So take, make it more generalized and from the use of limits. Then you introduce this idea and concepts of calculus. So if I take these concepts of pre-calculus, undergo this limit machine, and I get these concepts of calculus, well, there are two branches. There's the differential and integral calculus branches. And in these branches, using limits, we'll introduce different operations, if you will. And these will essentially start our studies in calculus. All right, so let's go ahead and look at a couple of situations. So to kind of introduce these concepts, on the graph on the left, we have the distance over time graph. So we want to find the velocity of a car at a specific time if it is traveling at a constant velocity. So if I look at this graph, you can see that the graph is basically changing at the same rate, per unit time, and so therefore we can say that it has a constant velocity. It's a non-dynamic graph. Now, if you look at the graph on the right, we want to do the same thing, but we want to find the velocity if it is accelerating. So in this case, since we have this word acceleration, we have a dynamic process, right? So this curve is definitely dynamic, and the distance changes, the rate of the distance changes over time. And that's what makes this curve more dynamic and more prone to the concepts of calculus. So the graph on the left, we can use traditional concepts that we have learned, using algebra or pre-calculus. And on the one on the right, it's going to take a more interesting approach, which involves, dealing with dynamic curves. All right, so if I look at the situation that we discussed, we have, let's say, distance versus time. And we'll say that distance is x and time is t. So if I want to find the velocity of a car at a specific time, well, I need to pick 2 points on the graph, and is essentially finding the slope. So if we take the rise over run, that gives us the difference in the x's over the difference in the times, t. And that slope will actually give us the velocity, because if you recall, velocity is distance over time. So, or in this case, the magnitude of velocity, which is the speed, is the distance over time. So it's change in x over change in t. So we identify our x1, x2, and our t1 and t2, and then take the difference in those values, and that gives us the slope, which is the magnitude of velocity. All right, and in this case, what we do is, we have this slope triangle. So just to kind of remind you, it's essentially finding the slope. And so velocity is the same everywhere, notice. No matter which 2 points I take on this curve, the rise or run, the slope, the rate of change is going to be the same. And so if I take the velocity at this point, which we can call v1, and I take the velocity at this point, which we can call v2, it doesn't really matter, right? The slope is the same, because if I do the rise or run, it's going to be the same for both points. And so we could say that the velocities are the same at any time. So velocity 1 is equal to velocity 2. All right, so using the concepts of calculus, if I want to find the velocity of this curve, what we need to do is introduce the idea of finding the slope at a single point. Before, we needed 2 points in order to make, 2 points in order to find, for example, the slope of a line. In this case, we have a curve, and if we want to find the velocity at a specific point, we need to introduce the idea of slope at a single point. which we'll do in more in a future lesson. But the main idea here is to draw what is called a tangent line. So notice that the velocity is not the same at those 2 points indicated. And we'll show that in a second. So at T1 and T2, we'll call those T1 and T2, and I cannot find the slope at a single point without introducing this idea of a tangent line. So what we need to do, if I want to find the slope at that specific point T1, I draw a tangent line, which is a line that is touching the curve at a single point and nowhere else. And then I can find the slope of this line, and the slope of this line gives me the slope at that point. So the rate of change at that point T1. And so let's call that slope V1 because that tangent line has to do with time T1. All right, and then if we look at T2, if we draw a tangent line that touches only at that point T2, then we could find the slope of that tangent line, and let's call that V2 for velocity 2. And notice that the slopes are different. They're actually not even pointing in the same direction. Slope V1 is in the negative direction and V2 is in the positive direction. So they're not even in the same direction. Now this idea, this concept of the tangent line is known as the tangent line problem. And it's one of the the first concepts that we'll talk about once we introduce limits. After we get through the limits process and review that, we're going to talk about this tangent line problem and introduce the concept of the derivative. All right, so to summarize, the pre-calculus concept is on the left. The curve is non-dynamic and it's traveling at a constant velocity. And we can do this by finding the slope of the curve, taking any 2 points and then finding the slope. And then if I ask for a specific velocity, at this point, for example, well, then we know that whatever that is has to be the same velocity as, for example, this point, because it's on the same graph, which is a line, and it's traveling at a constant velocity. And so in this case, V1 would be equal to V2. That's what we were saying, anywhere. And in fact, if I had a V3 here, that would also be equal to V3. All right, and then for on the right side, we said is more dynamic, and so the velocity, it actually varies over time. So the slope of the tangent line changes. So in here, the slope of the tangent line, the tangent line might be flat, and therefore the velocity at this time, let's call this time 1, the velocity at time 1 is going to be 0 because it's a flat line. Whereas if I do the velocity, here, if I draw, for example, let's say, let's do like over here, this is time T2, well, then I'd have to draw a tangent line there, and that tangent line, that velocity is going to be positive, right? So on one side, you got the velocity as 0, and on the other side, you have the velocity to be positive, right? So the velocity varies over time, and it's obtained by taking the slope of the tangent line at time t. All right, this part of the branch is differential calculus, and in this part of the branch, when we get to this chapter, we'll introduce the idea of the derivative. So let's look at an example. So a car is traveling with constant velocity, as indicated by the position versus time graph below. Using the information provided, determine the velocity of the car. What does the graph indicate about what is happening in this situation? So if I look at the position versus time, I want to keep in mind, well, first off, I need to do find the slope, right? So that's going to give me the velocity. And the easiest points to choose are obviously these ones here, that one, and this one. Those are the easiest ones because that's the y and x intercept. And so if I use those 2 points, I can get the rise over run to change in x over change in t. So let's go ahead and calculate that. So we'll call this, for example, if we call this T2 and T1, T1. Yeah, we'll call this right here, this point T1, we'll call this T2, and we'll call this height V1 and this height V2. And if we do that, if we plug it into the formula, we would get 0 minus 30, which is negative 30. and then 5 minus 0 for the times. And so we get a velocity that's -6 meters per second. So it makes sense, it's a graph going down, so the velocity is going to be in the negative direction. So what this indicates is that the car is slowing down, right? From time 0 to time 5 seconds, the car is actually slowing down or braking at a constant velocity. All right, so let's look at a more dynamic situation. So if I look at this graph, this is a voltage across a circuit element over a period of time. We want to estimate the rate at which the voltage changes at t equals 60 seconds. Now, we're going to use the word estimate because this is actually a calculus situation. If we knew the graph or the function of this curve, we can actually find the specific, the specific rate at a specific time. But here we need to use ideas of pre-calculus, right? Using slope and so on in order to estimate this. So notice that the graph is dynamic. And so what we're going to do is we're going to estimate. We're going to draw an approximate tangent line, right? So, drawing this tangent line, this is just an approximation here. So if I look at 60 seconds and I mark that point on the graph, then let's say I drew that tangent line. And so we want to find the slope of that tangent line. So let's pick that point right there as the second point. This point on the y-axis here. And let's say that's about 7. So it's about 7 volts for the voltage. So if I find the slope of that and I calculate the rate, so that's going to be the change in voltage or change in time. So then the change in voltage is from 7 volts to 10 volts, so 10 minus 7. And then from 0 seconds to 60 seconds, so 60 minus 0. And then we can calculate our rate, our estimation. And so the estimation is about 0.05 volts per second. And notice that rate is going to change over time. So it's going to actually slow down if I'm, for example, here. If I make that tangent line, that's almost flat, right? So the tangent line is getting flatter over time, whereas here the rate actually changes pretty quickly. Look how steep that rate is at the beginning of the curve. All right, so that is a tangent line problem. We're going to introduce another type of problem. So let's look at, so on one on the left, we have a car starts at position x equals 0 at time t equals 0. We want to find the displacement of the car traveling over the time period from t equals 0 to t equals 5 seconds. All right, so in this situation, notice that the graph is essentially just straight lines, right? So this graph is not dynamic. It does change over different periods of time, but if we take those chunks and just kind of focus on them separately, so if I just focus on this chunk, right, and then this chunk, for example, each of those are non-dynamic in nature, and we can focus on them and then just kind of combine them together, right? So this is a more non-dynamic situation. So we can use pre-calculus in order to do this, essentially. The one on the right is definitely more dynamic, and it's curvy, and it has some more complicated situations. So here, let's say we want to find the displacement of the car from 0 to 5 seconds the same way. That involves some calculus that which we'll discuss. So first off, before we tackle the problem on the left, we are going to kind of go over some situations of how to actually calculate the displacement. So notice that this graph is velocity versus time, whereas before it was distance over time. And there's a reason for that. If you have a graph with velocity versus time, there's a way that you can get displacement from that curve, which we'll discuss. So let's take a look at the first situation. So before we tackle the situation on the left, let's cover some situations here. Let's say I have a velocity versus time graph where I just have this period of time from 2 seconds to 6 seconds, and I want to find the displacement of the car. Well, in that case, in order to do that, well, first off, we know that velocity is distance over time. That's what we talked about in the first concept, right? Which is the tangent line problem. So it's change in x over change in time. However, we want to do this in terms of velocity versus time, right? So what we're going to do is we're going to solve. We're going to essentially move the delta t over to the other side. So we're going to solve for a change in x. And so we have change in x equals the average velocity times the change in time. And notice that I changed this to average velocity, right? Because that's what it is. Essentially, it's an average velocity if you're taking it between 2 points. All right, so in this case, we have change in x is average velocity times change in time. And again, we multiplied by delta t on both sides in order to get that. All right, so now we know that to get average velocity, we would have to, average velocity is essentially just adding the two velocities and then dividing it by 2. So this is for a line, right? So if I have a line, I can take the average velocity by just simply adding the two velocities, dividing it by 2, right? So for any simple curve, this is going to work, right? So if in this case, we know that the velocity here, which we'll call v0, is 6 meters per second because it's right on the 6th line, but the velocity here is also 6. So if I add those up, divide by 2, I get 6 meters per second. If I want to get the displacement, delta x, well, I can take the average velocity, right, which we said was 6 meters per second. And so we plug that in, and we know that the change in time is 6 minus 2 seconds. That's this change in time right here. We multiply those and we get 24 meters. All right, so what that indicates is that this displacement is 24 meters. And notice that that is the area of the rectangle under the curve. So if I take 4 and I multiply that by 6, well, 6 times 4, that's the area of the curve, right? The area of a rectangle is base times height, so it's going to be 4 times 6. So essentially, the change in x is equal to this area under the curve. And notice that the units can't work out, the seconds cancels, and leaves us with a displacement, right? Which is sort of like the distance, the net displacement the car traveled. All right, so we're going to look at another situation. So let's take a look at this situation. This time, what we have is, and this should say this is velocity versus time. So let's say that's v of t for velocity, where the velocity varies over time, and this is just going to be time. All right, time t. So let's say if I have that situation, well, we know this equation is change in x equals average velocity times change in time. So let's say this is v0 and this is v1. Well, in this case, v0 is 0 meters per second and v1 is 6 meters per second, right? And so if I take the average velocity over that time period from 2 to 6 seconds, which is a time period of 4 seconds, right? Well, then so 0 plus 6 divided by 2 is 3 meters per second. So we got the average velocity. And if I plug that in, the average velocity into the average velocity equation, or the displacement equation, then you got 3 times 4, which is 12. But notice that this is the area of the triangle under the curve. So if I find the area of this triangle, well, the area of that triangle is 1/2 base times height, right? And the base of the triangle is 4. And the height of the triangle is, well, it's this height here, which is 6, which is exactly the same answer, 12 meters. So 12, so which is actually equal to change in x. All right, so the area under the curve gives us the magnitude of the displacement here. All right, so let's look at one more situation, at least one more. So let's say the line is up here. Before, the line was down at the bottom. So what this does, it changes the situation a little bit, because now if we find the average velocity, well, now v0 is actually 6, right? And v1 is actually 10 meters per second. That's going to change the average velocity, right? So then in that case, the average velocity is 8 meters per second. And then if I plug that in to the average velocity, or to the displacement equation for average velocity, over the same time period of 4 seconds, right? The change in time is 4. I'd get a displacement of 32 meters. All right, so let's actually calculate this. This is actually the area of the trapezoid under the curve. So if I look at this curve, if I look at this area under the curve, it forms a trapezoid. And hopefully you can kind of see that, right? It's a trapezoid where these two are parallel. and then you have the other two. So it's sort of like a sideways trapezoid. So if I were to rotate it, you know, this is like the graph, right? Where this is V0, this is V1. It's sort of sideways. So it's a trapezoid. And to get the area of a trapezoid, right? The area of a trapezoid is equal to 1/2 times the height times your base 1 plus base 2. Where in your trapezoid, you have your base 1, you have your base 2, your parallel bases, and then you have your height. Well, in this case, it's the same idea. You have your height of your trapezoid is actually your delta t. So this is actually your height right here. And you have your base 1 and you have your base 2 here. Well, your base 1 is equal to V0 because it's 6 meters per second. Your base 2 is actually equal to V1, right? So essentially it's the same thing, right? You have 6 plus 10, so 1/2 times the height was 4. And then you have base 1, which is 6, plus base 2, which is 10. And then if you calculate that, you're going to get 32, which is equal to the area under the curve, which is equal to the displacement. So we're seeing a pattern here. We're seeing that in order to find the displacement of a velocity versus time graph, right, we need to find the area under the curve. So this is the idea. So if I take this situation, now this time, this one I believe is a little different. This is a trapezoid. So this is the final situation. We have a trapezoid, like this trapezoid shape, right? But it's not symmetric in any way, right? So it's an interesting situation. So let's take a look at it. So if I were to calculate this using the concept of average velocity times time, well then first off, what I'm going to do is I'm going to separate it into 3 regions. We have the average velocity 1 region, average velocity 2 region, average velocity 3 region. So we're essentially, these 3 regions are the other situations we looked at before. All right, so if I were to take the average velocity for 1, well, this is 0 meters per second, right? And this here is 4 meters per second. That's the value of the y coordinate. And so if I take the average, that's going to be 2 meters per second. If I do this for this one, this is 4 meters per second as well, where the average of 4 and 4 is 4. And the average velocity for 3, well, that's 4, and this is 0. So it's going to be 2 meters per second, just like it was for, the other one. However, keep in mind that, yeah, this is just the average velocity if we just look at, those coordinates, right? If I just look at the velocity, well, I can just say that that's the average velocity. However, what we want to do now is put this into an overall average velocity. So what's the average velocity of this curve, right? That's what we want to find. And so in order to do that, what we need to do is we need to incorporate each of these regions, region 1, region 2, region 3. And what we need to do is do a weighted average, because notice that in region 1, the average velocity, yeah, it's 2 meters per second, but it's only for a time period of 2 seconds, right? Whereas the average velocity for the third part is also 2 meters per second, but it's over a time period of 4 seconds. So of course that's going to change the result, right? If I average that with, for example, this one, which is 4 meters per second, but for a time period of 2 seconds, right? For the second average velocity. And so we're going to do a weighted average. So this is a weighted average velocity. So we're going to take essentially we're going to take the first velocity times the time that it takes, right? The time period that it takes, and then do the same thing for all of them. How long do they take in that average velocity over that section of the curve? And then we divide by the total time period of the curve. And that gives us our average velocity for the entire curve. So if I do that, well, notice that average velocity 1 is, the V1 is 2, the average for the second part is 4, and so on. And the time period for this one is 2 seconds. That's just 2 seconds here. The time period for the second one is 2 seconds, and then the time period for the other one is 4 seconds. So if I plug those in for my average velocity, for example, in the time period, and then I calculate the average for the whole curve, I get 20/8 meters per second. All right, and of course I can reduce it, but I'm not going to reduce it because what I'm going to do is I'm going to plug this into the displacement. So the displacement is average velocity times change in time. Well, the change in time is the time period of 8 seconds, right? For the entire curve. And the average velocity for the entire curve is 20 over 8. So we're going to multiply those together, and notice that the 8's cancel out, leaving me with 20 meters. All right, so we know how to do this using that, but we can also, now we know that we can find the area under the curve, right? If I find the area of this trapezoid, I should get the same thing, right? So if I look at, we know that the displacement is 20 meters. This is the area of the trapezoid under the curve. So we know that area of trapezoid, 1/2 height, base 1 plus base 2. Well, in that case, well, let's do that. Let's do that over here. The height of this trapezoid is this right here, right? So the height is 4. So we got 1/2 times 4. And we got base 1. Well, this is base 1, which is 8, because it's 10 minus 2. That's the length of that base. And then base 2 here is a distance of 2. So we got 8 plus 2. So we got 10 divided by 2 times 4, which gives us 20. Which is exactly the same as the displacement we got earlier. So in other words, to find the displacement, we need to calculate the area under the velocity versus time curve. So I showed you several situations in which this works. Let's look at a situation where the graph is negative. So if the graph is going down, what happens about that? So we've only looked at where it's above the x-axis, but what if it's below the x-axis? Well, this also works for negative values, right? So let's show you how to do this. We're going to break this into 3 sections, and the area of the first part, to find the displacement delta x1, well, that's just the area of this square, right? So we have this square here where, you know, the height is 4 and then the base is 4. So the area of the square is 16, right? 4 times 4, which is 16 meters. And then we have the area of the triangle for the second one, which is 1/2 base times height. We know the base here is 3, and then the height is 4. So 1/2 times 4 times 3. And then the one in the triangle here, right? We know that the height is, well, this position is -3, right? So we're saying negative because it's going down below the curve. And I know we're saying area, and it doesn't make sense for area to be negative. So what we're doing is we wanted the magnitude of the area, but we're going to include a sign in there, positive or negative, right? And negative doesn't necessarily mean the area is negative, but remember, we're attaching this to the idea of displacement. And so displacement is -3, but the area itself is 3, all right? But we'll say that area is negative, just to simplify the argument. So we have -3 because it's below the x-axis, and here this is 2, and so 1/2 base times height, that's -3. All right, and so if I do the net displacement, I just have to add these 3 displacements, which gives me 19 meters. And so that displacement of -3 you see here indicates that the car, so what happens is that the car had the same velocity, right, for 4 seconds. So it had the same velocity. So the car was traveling at a constant distance, versus time, like the rate is constant. Then the car slows down, right? The car is slowing down because velocity is negative. The car is braking. At 7 seconds, the velocity of the car is 0, which means the car here is at rest. And then afterwards, the car continues going, having a negative velocity. So here the car is braking. From this time period to this time period, the car is actually putting the brakes, right? But then in this time period, the car is actually reversing. Because now it's losing the displacement, it's losing distance, so it's actually going in reverse. So that's why it's taken away from the displacement. So overall, it got displaced 19. All right, so let's go back to the original situation that we had. Now that we know how to tackle this situation, let's go ahead and do it. So we want it from 0 to 5 seconds, if you recall, and we had this graph here. We only want it for that 5-second period. Well, we know that delta x1 is going to be 0 because the car is not moving at all. And we know the average velocity is this, that's the average velocity, but we know that here it's 0 and here it's 0. And so the average velocity is 0, but 0 times this time period of 3 is going to be 0. So delta x1 is equal to 0. And delta x2, we know that this is 0, this is 8, and so 0 plus 8 divided by 2 is 4. And then from here to here, it's 2 seconds. So then 4 times 2 is going to give us 8. All right, if I add those two displacements together, I get a total displacement of 8. So that's using the concepts of pre-calculus. No, nothing crazy here. It's just the ideas of physics and pre-calculus, right? Now let's take a look at the dynamic curve. So if I look at the dynamic version of this, and I'm going to do it from 0 to 5 seconds. Well, how do I do it? Well, because we're finding the exact area underneath the curve, because it's more dynamic, we're going to require integral calculus, which talks about this idea of the integral, which is a way to help you find the area under the curve, right? If we're talking about this situation. Well, without calculus, what we can do is we can estimate. So in this case, we're going to estimate with an area of a triangle. We want from 0 to 5 seconds, right? From this time period. And then we can draw this triangle, which is very close to the area under this curve, right? We want to get the area under this entire curve, which we have a tiny bit of error there. So let's go ahead and estimate it with that shape. In this case, well, we know that an area of a triangle is 1/2 base times height. In this case, the height here, this is about 41. If I look at this is, because these are going by 2s, I believe, 42, 44. Actually, if I look at this situation, yeah, we'll kind of guesstimate. It's a little bit above the 40, so I'm just going to guesstimate it to be about 41 or so. If you want to, this is just an estimate in any case. So let's say it's about 41. So then we have the height is 41 times 5. In that case, 1/2 base times height. So we get about 102.5. And again, this is just an estimate. Without calculus, we can only estimate, right? So even if I got the area of this triangle perfectly, it's still going to be an estimate because it's not the exact area under the curve, because we still got this little portion of the curve right here, which is not covered by the triangle. All right, so that's just an estimate. So what we're going to talk about, this situation that we're talking about is known as the area problem in calculus, right? And it's covered by the integral branch. So the area problem, how does it work? You take any curve f of x, right? And you can estimate the area under that curve by using, basic geometric shapes, right? That you can do with basic geometry, right? So triangles, rectangles, so on. In this case, the idea is we break it up into rectangles, and then we find the area of those rectangles, right? But notice if I find the areas of the rectangles the way it is here, we still got a little bit of area that's left over, right? That we need to find. And in fact, sometimes we have this area that pokes out, and that's actually messing up our accuracy as well. But the idea is you can use a limit process to create as many rectangles as you need to get the exact area under the curve. So this is known as the area problem and is part of the integral branch of calculus. So for example, if I wanted to make more rectangles here, well, I could, for example, make them smaller. And if I make them smaller, well, then guess what? I can cover more area under the curve. And then the idea is I make them as small as possible. If I make them even smaller, then I can cover more area. And then ideally, if I have an infinite amount of rectangles, well, then that's going to help me get the exact area under the curve. And that's known as the area problem. So we're going to use this idea in order to estimate that area. So let's looking at this example. We want to use rectangles to approximate the area under the curve y equals 5 over x between x equals 1, x equals 5, and the x-axis. So this curve is y equals 5 over x. And so we want to do it between x equals 1. So this is the graph. This is x equals 1, right? And then x equals 5. So we want to get the area between those two, and then bounded by this graph, of course. So essentially, you want to get this area. Well, if I do that, notice that if I draw those rectangles, it's not going to give me the exact area that I need, right? So the idea is we want to get that exact area, but we can't do that unless we have the concepts of calculus. So we're going to estimate. All right, here we go. So if I do the graph on the left, notice that. Let me erase all this stuff now. So if I do the graph on the left, the area of a rectangle is base times height. So notice that the area, and notice that the base of this rectangle is 2 minus 1, which is right here, right? Which is a 1. And the base of the second rectangle is 3 minus 2, which is also 1, right? So that's the base. So that's 1. The height of the rectangle is actually given by the position on the graph, the y-coordinate of the graph, in this case 5, right? So this 5 value is actually the height of this. So the height of the rectangle is actually f of 1 in this case, right? So that's f of 1, which is 5. So in this case we have 5. And then the height of the rectangle for the second rectangle is given by f of 2, which f of 2 is well, it's on the graph, and to get f of 2, we know that the function is 5 over x, so it's going to be 5 over 2 in this case. Okay, so, and then so on and so forth. So you can kind of see how to get the area. So that's how I got that. So we got 2 minus 1 times f of 1, and then we have f of 2, f of 3 for the second graph. That's the height here, and then f of 4. So then but we know that 2 minus 1 is 1, 3 minus 2, so these are all 1. So it leaves us with f of 1 plus f of 2 plus f of 3 plus f of 4. That's essentially just the height of the rectangle times an invisible 1 is my area. Well, then we know that f of 1 is 5 over 1 because the function is 5 over x, right? So it's f of 1, f of 2, f of 3. So 5 over x, 5 over 1, 5 over 2, 3, and 4. So if I add those, I get an area of 10.4. Remember, this is just an estimate. Now, if I take the graph on the right, well, this base is 0.5. It's 1 minus 1.5, right? Because this is these are going by 0.5s. So that's this here. That's 0.5. And then the height of the rectangle is f of 1, which we know is 5, right? The height of this rectangle is f of 1.5, whatever that is. It's somewhere between 3 and 4. But we know f of 1.5 is simply 5 over 1.5 because we know the function is f of x. All right, so and then so these are all going to be 0.5s at the end of the day. So if I look at this is going to be 0.5. These are all 0.5 times the height of the rectangle. So if I continue, we know that since these are all 0.5, we can actually factor those out, right? So we can factor those out of the expression and get 0.5 times each of these heights, f of 1, f of 1.5, and so on. And remember, there's a lot of rectangles because, so I put a dot, dot, dot here. So this is showing technically all of them. And then we know that f of 1 is 5 over 1, f of 1.5 is 5 over 1.5 because of the function, and f of 2 is 5 over 2, and so on. If I multiply those together and simplify that expression, I get 9.145. So notice that the area decreased, right? And that makes sense because here in the first situation, we highly overestimated the graph because of these, we have these portions here that are kind of overestimating what the actual area is. And then we have less of an overestimation, right? So the graph is actually, the area that we're finding is actually going down, which makes sense. It's getting more accurate. So if I repeat this process for n equals 4 rectangles, this is for n equals 4, the first situation that we looked at, this is n equals 8 rectangles. So as we double the amount of rectangles and we keep doing that, what's happening to the area? Well, this is the first situation, this is the second situation, the area is going down, but it's approaching something, right? The area is actually approaching a value. So notice that as the number of rectangles increases, the approximation of the area becomes better. Using calculus, we can actually get the exact area to be 5 times the natural log of 5, which is about 8.047. That's what the area should come down to. But we were pretty close, right? If we had 64 rectangles and we continue that process, we get pretty darn close to that area. And we'll talk about it when we get to this calculus lesson for finding area under the curve. We'll be able to get the exact area just like that. That is the end of the lesson, guys. Thank you for watching this video. This is just an introduction, so even if none of these concepts, the main concepts that we want to get across are the idea of the tangent line problem and the area problem, and just introducing you to those notions. And then we will take them in more details. So we'll talk about limits, and then we'll actually introduce those more calculus concepts, other calculus concepts, derivatives, integrals throughout the video series. Thank you for watching this video, guys. I hope you learned something as usual. I'll see you in the next one.